Hello, I am happy to introduce our new work on the effectiveness of parameter-efficient fine-tuning. I am Zihao Fu from the University of Cambridge. Our code is public on GitHub now. This is the outline of today's talk. I will first give an introduction of the fine-tuning model, and then I will give a unified view of parameter-efficient fine-tuning. Then I will discuss the theoretical analysis of the sparse fine-tuned model together with our newly proposed second-order approximation method. Finally, I will give some experimental results and our conclusions. Fine-tuning the model parameters for a specific task on a pre-trained model like BERT, Roberta GPT has become one of the most promising techniques for NLP in recent years. It achieves state-of-the-art performance on most of the NLP tasks. Unfortunately, as the parameter number grows exponentially to billions or even trillions, it becomes very inefficient to save the fully fine-tuned parameters. Many recent research works propose a parameter-efficient way to solve this problem. Parameter-efficient fine-tuning only tunes a small part of the original parameters and stores the tuned parameters for each task. It achieves significant storage efficiency. Currently, many parameter-efficient fine-tuning models have been proposed. We divide them into three categories, including random approaches, rule-based approaches, and projection-based approaches. The random approaches, including random model and mix-out model, they randomly decide which parameters to turn. The rule-based approaches use specific rules to decide which parameters to turn, but they do not utilize task-specific data information. The projection-based approaches trains all the parameters and projects them on a sparse region. It suffers from the project's discontinuity problem, which makes the parameter selection quite unstable. Currently, as a lot of parameter-efficient models achieve considerable success, two important questions remain to be answered. The first one is why parameter-efficient models achieve promising results. In this paper, we will show that it is the sparsity that helps improve the fine-tuning stability and thus improve overall performance. The second question is how to choose the tunable parameters. Currently, many approaches propose to find a proper set of tunable parameters, but they suffer from different problems. We propose a novel second-order approximation method to solve the problems, and we will show it achieves the best performance. Our contributions can be summarized as follows. First, we propose a new categorization scheme for existing parameter-efficient methods and generalize most of these methods with a unified view called the sparse fine-tuned model. Then, we show that most existing parameter-efficient models are sparse fine-tuned models. Second, we conduct a theoretical analysis of the parameter-efficient model's stability and generalization on sparse fine-tuned model. Therefore, our theory can be used to explain most of the existing parameter-efficient models. Third, we propose a novel SAM model to choose the most suitable parameters to optimize. It overcomes several problems in existing models. Finally, we conduct extensive experiments to verify our theoretical analysis and the SAM model. Now, let's take a look at the unified view of parameter-efficient fine-tuning. In this section, we first define the unified p-sparse fine-tuned model. It is simpler and easier for theoretical analysis. Then we divide existing parameter-efficient models into three categories based on how the parameters are chosen. Finally, we show that all the models are sparse fine-tuned models. This makes our theoretical analysis applicable to analyze more methods. Here is the definition of the p-sparse fine-tuned model. Intuitively, we say a model is a p-sparse fine-tuned model if it only fine-tunes a small portion of the pre-trained model. This is our categorization of most existing methods based on different strategies for choosing tunable parameters. This method can be divided into three categories, namely randomly approaches, rule-based approaches, and projection-based approaches. We will discuss why they are p-sparse fine-tuned models one by one. The random approaches randomly choose the parameters to be tuned. Such selection does not depend on task-specific data information. The random model is very straightforward. It randomly selects the parameters with respect to a given sparsity ratio and then trains the selected parameters. Therefore, it is a p-sparse fine-tuned model. The mix-out model directly receives a portion of the fine-tuned model's parameters to the pre-trained parameters with respect to a ratio. Therefore, it is also a p-sparse fine-tuned model. The rule-based approaches directly use a pre-trained rule to fix the parameters to be tuned. However, the selection rules are still irrelevant to the specific data. For example, the Bitfit model only fine-tunes the bias terms and achieves considerable good performance. Therefore, it is a p-sparse fine-tuned model. Mac pruning follows the idea that large weights are more important in the model. It tunes the parameters with a large norm. Therefore, it is a p-sparse fine-tuned model. Some rule-based approaches like adapter and LoRA add new structures into the pre-trained models. Therefore, the definition of the p-sparse model is not applicable to these scenarios. To solve this problem, we introduce an equivalent model to help with the analysis. Here is the definition of the equivalent model. We do not require that it shares the same structure as the original model. Therefore, adapter and LoRA in p-sparse fine-tuned models with respect to their equivalent model. As a result, our analysis of the sparse fine-tuned model is also applicable to them. The adapter model proposed to add an adapter layer inside the transformer layer. Therefore, the model structure is different from the original model. To make it easier to analyze, the adapter can be viewed as fine-tuning an equivalent model shown in Figure 1a. Therefore, fine-tuning the adapter model can be viewed as fine-tuning partial parameters of the equivalent model, and it is a p-sparse fine-tuned model. The LoRA model proposed to add a new vector calculated by recovering a hidden vector from a lower dimension space. The model is illustrated in Figure 1b. It is interesting to note that the zero initialization makes the LoRA model already an equivalent model because matrix B is set to 0. Therefore, fine-tuning a LoRA model can also be viewed as fine-tuning partial parameters of the equivalent model with the same structure. Projection-based approaches choose and optimize the parameters alternately. First, the deep pruning method proposed to model the parameter selection mask as a Bernoulli random variable and optimize the variable with a reparameterization method. It then projects and does the optimization alternately. Therefore, it is also a p-sparse fine-tuned model. On the other hand, the child pruning method iteratively trains the full model parameters and then calculates the projected mask to find the child network. Therefore, it is a p-sparse fine-tuned model. Projection-based methods suffer from the projection discontinuity problem. Specifically, the visible region of the mask is non-convex. Therefore, it does not have the non-expansion property, and a small perturbation on the mask can lead to a totally different projection. For example, here in this figure, a small perturbation makes M1 jumps to M2, but the projection of them are totally different. Now let's look at the theoretical analysis of the sparse fine-tuned model. We first give a definition of the pointwise hypothesis stability during the training. Here is the definition. Intuitively, give a small perturbation on the training set S, and we train the model again. We measure how the output of a specific sample will change. If it changes a lot, it means the training procedure is not stable, while if it is small, the model is more stable. With that definition, we can give the upper bound of the stability as shown in Theorem 1. It can be observed that as the sparsity parameter P decreases, the upper bound also decreases. Therefore, sparse models imply better stability. It can explain most of the empirical results in recent works. It should also be noted that if P is too small, the upper bound will not change significantly. Now, the denominator is denominated by lambda min, which is related to the landscape of the function. This is why empirically the stability is impaired. Let's further look at the generalization bound. This theorem tells us that the generalization error upper bound becomes small as the fine-tuned parameters become sparser. Intuitively, if a model is stable, a perturbation makes less effect on the model and the model is less likely to overfit. It should be noted that the generalization error bound is determined by both the empirical error and the sparsity. Therefore, as the mask becomes sparser, even though the second term decreases, the training error will possibly increase when the tunable parameters are not enough to fit the data. Consequently, as the sparsity decreases, the generalization will first decrease and then increase. Now let's look at our newly proposed second-order approximation methods. In the previous section, we have shown that the random and the rule-based approaches do not utilize the information from the task. specific data, and the projection-based approaches suffer from the projection discontinuity problem. To solve these problems, in this section, we propose a new approximate-based method to choose the tunable parameters. To solve the problems, we propose a novel second-order approximation method. It can utilize the data information to help decide the parameter mask while avoiding the projection discontinuity problem. We first approximate the loss function with its second-order Taylor expansion as shown here. Unfortunately, the Hessian matrix H is expensive to compute, especially for a large neural model. To solve this problem, we first approximate the Hessian matrix with a dialog matrix. We also assume that H is positive semi-definite because the pre-trained weights are close to the global minimizer. Then the optimization problem can be reformulated as follows. With the above settings, we can calculate the optimization parameter mask M for problem 4 based on this problem. It can be observed that selecting features according to this theorem achieves the minimal value of the approximation in problem 4. The remaining problem is how to calculate the dialog of the Hessian matrix. Unfortunately, calculating the dialog is as complex as calculating the whole Hessian. To solve this problem, instead of minimizing the target function in problem 4, we propose to optimize the upper bound shown in equation 6. Then we design our SAM method. It first gets the gradient for the ith parameter I. Then it calculates the absolute value and takes the parameters with largest norm to optimize. Afterwards, it optimizes the selected parameters and gets the fine-tuned model. Now let's look at some experimental results. This table shows the main experimental results. We can draw the following conclusions. First, most of the parameter-efficient models achieve better performance than the full fine-tuning model, which is also consistent with observations in many previous works. Second, most of the parameter-efficient models are more stable than full-tuning model. Besides, it is interesting to note that even the random model outperforms the full-tuning model. It shows that sparsity itself contributes to improve the performance. Finally, our proposed SAM model outperforms several baseline models. This observation validates the effectiveness of our parameter selecting method. We conduct a new experiment to illustrate the projection discontinuity problem. We adjust the mask every 600 training steps. It can be observed from the figure that each time we change the mask, the training error will go back to almost the same value as its initial value. This result shows that changing the mask severely affects the training procedure due to the projection discontinuity problem. We also conduct an experiment to show the relationship between stability and generalization. Here is the result. The x-axis is the stability rank and the y-axis is the corresponding overall performance rank. It can be observed that they are positively correlated. We also report Spearman's rank correlation coefficient to show the significance. This experiment shows how the overall performance and the stability change as we change the sparsity. It can be concluded from the results that first, as the sparsity ratio decreases, the models become more stable with better generalization. It verifies with prediction in theorem 1 and 2. Besides, if the sparsity ratio drops below the certain threshold, the models become quite unstable and the performance also see a sharp drop. This is consistent with our previous discussion in theorem 1 and 2. We also conduct a new experiment to verify the data perturbation stability. We train the model on different sampled training set. It can be observed from the results that when we impose perturbation on the dataset, our proposed SAM model still has the best stability and overall performance. Now let's draw some conclusions. We can draw some conclusions for today's talk. First, we propose a new categorization scheme for existing parameter-efficient method and generalize most of this method with a unified view called the sparse fine-tuned model. Second, we conduct a theoretical analysis of the parameter-efficient model stability and generalization. Third, we propose a novel SAM model to choose the most suitable parameters to optimize. It overcomes several problems in existing models. Finally, we conduct extensive experiments to verify our theoretical analysis and the SAM model. Just get more information in our paper and our code on GitHub. Thank you.